Hello, this video is going to go over how to sketch parent exponential functions, their transformations, and how those sketches will end up looking. So before we start, we're going to discuss the parent exponential graphs. So meaning we have as simple as possible exponential, so base is a constant, exponent is the variable. So we're going to discuss and show what kind of graph you will have if the base is 1, if the base is between 0 and 1, higher than 1, or negative. So let's start with the first one. If base is equal to 1, so using Desmos here, if b is exactly 1, we have this line over here. And so if you wanted to create a table of values, if you didn't have Desmos, you could do this by hand. You could say, well, any x value you wish, put it into the exponent of 1 to the power of 2, which stays 1. Or another x value that you could choose is 1, so 1 to the power of 1 is also 1. 0 could be chosen, so anything to power 0 is 1. A negative exponent could be used, is still 1. So you could see that it's going to be a flat line, which is not considered an exponential graph. So let's move on to another type. So if the base is between 0 and 1, so for example, here we have 0.6. So this is a table of values for the one that's already done in Desmos. So what we're going to do is take a look at another base that is also smaller than 1, but positive. So 0.25. So if we put any values for x that you wish, I usually tell students to choose some positives and some negatives and put them into your parent equation. So 0.25 squared would be approximately 0.06 and so on. So if you took all of these numbers and plotted them, you would have again this graph, which from left to right looks like it's falling. So we call this graph graph of decay. So both of these 0.6 to the x and 0.25 to the x, or any base that is between 0 and 1, is going to be a decay graph. Notice for both of them that they have y-intercept at 1, and both of them approach on the right side to a horizontal asymptote of y equals 0. So what that means is that the graph is going to get closer and closer to 0, but never really reach it. Let's move on to another type. If the base happens to be bigger than 1. So this particular one done on Desmos is base 2.2. So these are the numbers that you could use, and those numbers match exactly to this graph already shown. For comparison's sake, I'm going to do another one, 3 to the power of 2, or sorry, 3 power x. So again, this base is above 1, so it matches this category. So choosing any x's we wish, so some positives, some negatives, and a 0, we get these results. If you were to plot them, we get this graph right here. Again, just like the other one, they both have similarities, so they both go through y-intercept of 1. They still have the horizontal asymptote at 0, but this time it's on this edge instead of on the right edge. And when you read this from left to right, both of these graphs will rise. So we call it the growth graph. So if the base is bigger than 1, we're going to have an exponential growth. Finally, what happens if the base happens to be negative, below 0? To take a look at that, again, let's choose a number that's below 0. So for example, negative 2 as the base, power x. Choose some positives for the x, some negatives, and a 0. Put them into the equation to find out your outputs. Then plot them. Here's the weird part that happens here. We're going to have some positives. For example, this negative 2 squared, anything squared is positive, so we have positive 4. And then negative 2 as an exponent just makes it reciprocal, but it's still going to be squared, so it's also positive. So there's a bunch of positives and also negatives. So it's going to bounce up and down, up and down, up and down. That's not the only weird part. The other weird part is that there are numbers in between each of these integers for x's. So imagine we took a number that, let's say, 0.5 or a half. And if we put 0.5 as the exponent, then -2 to the power of 0.5 is equivalent to having a fraction 1/2 as an exponent, which we have learned is a square root. And with real numbers, square root of a negative does not exist. It gives us an error. So there will be a bunch of gaps between each of these dots. So all that to say that we will not study this last version because it doesn't give us a smooth continuous graph. We will not study the first version either because it's too boring. It's just a flat graph at 1. What we will study is these two right here. Okay, so I cross those two off. And so the two that we will study, if the base is very close to 1, is going to be more flat graph, closer to the base being 1 itself, except it wouldn't be if it's not exactly 1. And if the base is closer to the 0 number or to infinity number, it will hug the axis more, but it will either grow or decay. So this one, with base smaller than 1, it will be decaying, and bases bigger than 1 is going to be growing. So the summary of key information about growth and decay parent graphs. This is before we introduce transformations. This is just talking about the basic shape. So we could have a growth, as we said on previous slide, that if base is greater than 1, it's going to be growth, and it's going to rise from left to right, have a y-intercept of 1 and horizontal asymptote. HA stands for horizontal asymptote at 0. Its domain and range is written here. And for decay, we want to be below 1, but not below 0. So it has to be positive, but between 0 and 1. And here the graph is going to fall from left to right. It will still have a y-intercept of 1, and it will still have horizontal asymptote at 0. And these are the domain and range for this. So both of domain and range for growth and decay end up being identical. Of course, these characteristics of y-intercept, horizontal asymptotes, domain and range, they will start changing as soon as you start to transform this, reflect them, shift them, stretch or compress them. So let's tackle a question where we have transformations applied. I'm going to show it to you in two methods. Method number 1 is going to be identifying the parent using its table. Then once we find the transformations, we're going to apply them to the table from the parent. This method is what you have learned in the general functions unit. This is a method that works for any function that you're given. I will talk about a method number 2 that is more convenient to use for exponential graphs, but it only works for the exponential graphs. It would not be applicable to trig graphs or other. So method number 1, that's applicable to all types of graphs. What we're going to do is identify what the parent function is. So you're going to locate the base where the exponent is located. So here we have 4, and then just the exponent x is going to be our parent. And we can create a table for this parent by plugging in any positives, a 0 and some negative values for x's, and figuring out the corresponding outputs. To see the transformations, we want to potentially rewrite this format of the exponent a little bit so that it matches more to this form in general. We want to have a constant multiple or coefficient on the x, and the way it's written here with a fraction is not as obvious what that constant would be. But if you put in 1/2, dividing by 2 is the same thing as multiplying by 1/2, then it's more clear that this 1/2 is the corresponding coefficient on the x. And so matching things up, anything that's a multiple outside of the function, so outside of our parent function, multiple is -192. That will control a reflection in the x-axis, as we've learned before, and because this number 192 is bigger than 1, it's going to vertically stretch our graph. Then any multiple inside of the function itself, so inside of the exponent, we have a multiple of 1/2. That's going to be a horizontal stretch. So if the number was bigger than 1, we will say horizontal compression, but because it's smaller than 1, we'll say a stretch. Again, this is review from functions unit. Then the number that's being added or subtracted inside of the function, we call it the d, although you don't have to call it with these specific letters. So inside of the function, meaning inside of the exponent, we have a subtraction of 6. So the d actually is a positive 6. And being positive is going to shift it to the right. And then a number outside of a function that's added or subtracted would be shifts up or down. And then here we have subtract 10, and that's a shift down. After finding the transformations, we want to be able to apply them. And to apply them, the best way to explain it is to do it all in one go, in my opinion, by just following this mapping formula. Let's start with the y coordinate. So all of these y values that we have here, 16, 4, 1, a quarter, etc., we're going to multiply all of them by the a, which is negative 192, and add c, which is subtract 10 for us. And that's going to give us the new coordinates in the table. So this is what the table is going to look like. We have negative 192 times y, subtract 10. So let's just talk about this first one. Where did that come from? So if you take 16, you multiply it by negative 192, subtract 10 from it, you will get this number. Then if you take 4, multiply by negative 192, and subtract 10, you would get this next number, and so on. So that explains the y's. Where did that come from? Well, if you actually look at the formula in general, we have a is multiplied by this output. So I'm circling right now this right here. This is the whole output. And we call the output as the y, and then plus c. So this is basically what this general function is saying anyways. For the x, though, it is opposite of what you might think. Just like in the equation, if you had minus 6, it's actually going to the right, it's opposite. Same thing happens for everything to do with the input. So in general, we have a multiplication of k on the axis. What we're going to be doing is dividing by that k. If we have subtraction written in the equation, we're actually going to be doing the addition. So in our situation, k is a half. So we're going to take all of these x values, and we're going to divide them by a half and add 6 to move it to the right. So let's try a few of them. So 2 divided by a half, it's like multiplying by 2, so that's 4, plus 6, that's 10. Then you do the same thing with 1. 1 divided by a half, that's like a 2, add 6, that's 8, and so on. And once you have this table, I would suggest that you also perform these operations on the horizontal asymptote as well. So don't just do positives, 0, and negatives for the x's. Add in one more row, call it horizontal asymptote, and in the y position put y equals 0, because horizontal asymptote is at 0 for the parent one. However, because we have transformations, this horizontal asymptote will change here to a different number. How does it change? You perform this formula on it like before. You take 0, you multiply it by negative 192, and subtract 10, you would get negative 10. Some of these numbers are too huge to plot, so I just plotted the horizontal asymptote here, and I put in the point 2 with negative 22, and then it just keeps going downwards from there. Let's talk about method number 2. So I've kept the picture that we had from method number 1 as comparisons. So this particular method only works for exponential functions, growth or decay, but it would not work for quadratics or some trig functions that we're going to be studying in a bit. So what we want to do is utilize exponent laws to simplify this expression. So instead of the exponent being so crazy looking, the exponent will be just x. So let's go to the side over here. And instead of division by 2, we can have multiplication by a half. Same thing. Then I'm going to remind you of this power of a power law. If we have 2 exponents on the same base, we can multiply them. Please know that we can also go backwards. So if they were already multiplied here, we can separate them and put part of it inside of the bracket. That's what I'm going to do here. I'm going to take this 1/2 and put it inside of the bracket, so just regrouping it a little bit. Well, square root of 4, because that's what 1/2 is, it's a square root. Square root of 4 is just a 2, so we can simplify that. Next, the exponent is not just x yet. That's our goal, just x as an exponent. We're going to talk about one more law. If we have 2 same bases multiplied, then we can add the exponents. But we're going to apply this law going in the other direction. If you have a binomial exponent on a single base, we can write down 2 of those bases and those 2 exponents separately. This is what I mean. So this 2 to the x and another 2 with -6 is equivalent to the line above. Why is this helpful? Well, this 2 with a -6 could be written on the bottom because it's a negative exponent, and you could put it along with 192 because these all of them are numeric, so you can simplify these numbers. And now we have base to the power only x. On the side here, I have 2 to the 6 is 64, so as you're simplifying, this in the end ends up being a very simple equation to work with, unlike the original. So it's a give and take. So either you have to be really good with exponent laws, and then it makes it really easy to sketch, or you have to remember all those steps of method 1. So it's really up to you how you apply these. Just be comfortable and practice lots. So now how do we sketch this in a faster way? You identify your new parent. So notice it's not 2 to the x anymore, or sorry, not 4 to the x anymore like the original. We have a new parent base now. It's 2 to the x. So looking at your simplified, parent is 2 to the x. We have our transformations as before, but we're not going to use them. I just list them here to show you that they're a little bit different than we had before. They're still equivalent. And the parent, usually, all parent functions are always size 1 from the y-intercept down to horizontal asymptote, right? So in this situation, I want you to see that there is definitely a reflection in our graph. There's definitely a shift down, but there's also a vertical stretch as well of 3. So if you look over here, this size as an arrow here, that would be a size of 3. And it's negative because it's going down. So all of these are visible, but I prefer not to even use transformations unless I specifically say state transformations. You don't have to use this concept. Let me show you what's the better way. So if you have a simplified version like this, meaning the x is the only thing in the exponent, you don't have a k or a d, then here are the key aspects. The horizontal asymptote will always be this plus c, so that's easy. The y-intercept is going to be very simple. To find the y-intercept, all we have to do is plug 0 on the x. So imagine b to the 0, that's just 1, so a plus c is the result. Then, all you have to do is ask yourself, for looking at the base, whether that's growth or decay, and then also ask yourself, were there any reflections in our question that would cause this growth or decay to swap? Let's actually do that on our question. Okay, so we have a horizontal asymptote at -10. Okay, so draw it in. Let's find the y-intercept, plugging in 0 for x. Simplifying, 2 to the 0 is just 1, so we have a -3 times 1, which is -3. Subtract 10 is -13. We could plot that there. So just like before, we already mentioned that size is 3, so here it's shown. After you've done those two things, then you ask yourself, what about the original? Original parent. When I say original, I mean original simplified parent before we applied these transformations on them. So this parent, the base here, 2, is bigger than 1. So it is growth, like we already had a little picture here. But because of this reflection, it's going to now fall from left to right instead of grow or rise from left to right. So it's going to fall from left to right. And you can see how this shows pretty much the same shape, just with a different point focus. All right. I feel like we need another example just to make sure that we're good with this. So here's another example. I have kept the key information on the bottom for us. So first, let's start by simplifying this. So we have two terms in the exponent, so rewrite them using two bases. So 4 to the 6 and 4 to the negative 3x is equivalent to the line above. Then 4 to the 6 could be evaluated. And then on this side, we're going to use power of a power law going backwards. So put this negative 3 as part of this base itself, which we can work out on the next line. 4 to the negative 3 is the same thing as 1 over 4 to the power of positive 3. And half of this number here, we can simplify that as well. And finally, because this is going to be just a sketch, you don't have to leave things as fractions. You could go into decimals, but if you are rounding, make sure you put equals with a little dot to indicate there is now approximation happening here. Once you have written it in that format, identify your horizontal asymptote, which is your addition at the end, so 8. Identify your y-intercept. Plug in 0 into the exponent. Simplify that, you get this number. Do a bit of a sketch here, and I know the scale is completely wonky here. Size 8 comparison to this almost over 2000, but just make sure you label everything, and that's fine. Then last step, identify whether what you had in the simplified version, original parent graph would be this base to the x. So this is base to the x. This base happens to be lower than 1. And this lower than 1 is going to cause it to decay like this. So this picture is just for this parent function. Now all you have to ask yourself, will this shape reflect or not? So you look at your negative in your simplified version, there is a reflection. So the decay, instead of falling from left to right, our graph is going to grow or rise from left to right. So it has to go through this point over here for the y-intercept. It has to approach the horizontal asymptote, and it's supposed to rise growth from left to right. And so you can finish off the graph, and that's it.